Welcome to our presentation. Our assignment topic is about sugar production industry process done by Group 4 featuring Zhengwei, Nafal, Tristan, Danish and myself, Jed. Next slide. Firstly, a little background of sugar production. Sugar is an old commodity which is commonly produced from sugarcane and sugar beet. There's 120 nations in total involved in sugar production industry, where the top 10 nations contribute to 2/3 of total sugar produced worldwide. The table on the next slide will show the production of the top 10 countries. Aside from socio-economic contribution, sugar production is a worthy agriculture crop because it also contributes to energy refuel and chemical synthesis. So it plays a major role in changing the physical-chemical characterization of an ecosystem. Next slide, please. So in table 1, as you can see, it actually summarizes the ranking of the top 10 countries involved in sugar production and the sugar produced in metric tons and their contribution to the sugar production percentage internationally. It's no surprise that India is the leading manufacturer of sugar production. Next slide, please. There are two general manufacturing process, carbonation and sulfitation process, with the latter being more economical and widely used. Major operation units include sugarcane crushing, juice clarification, crystallization, centrifugation, depolarization and conditioning, and finally packing and bagging. To start off, sugarcane are first collected from agricultural plantation. The stock materials are transported and stored in a warehouse or sugar processing plant. Subsequently, the sugar cans are transferred on a conveyor into a sugarcane crushing compartment.
This is the process flow for sugarcane, which are planting and harvesting, preparation and processing, juice extraction, purification of juice, crystallization, centrifuging, drying, and packaging. This is the process diagram that shows the processes that are used to turn sugarcane into sugar. Next slide, please. The first major unit operation is preparation and processing. Sugarcane is washed with warm water to remove the impurities like mud, oil, grease, and etc. They are cut into small pieces using cutting machine and sent to the rolling mill to squeeze and extract the sugarcane juice. Extracted juice is transferred into juice clarifiers and unserviceable pressed sugarcane for purification. Next slide, please. The second major unit operation is clarification. The clarification process is designed to remove both soluble and insoluble impurities that have not been removed by preliminary screening. Clarification is done exclusively with heat and lime. Lime is added to neutralize organic acids. This process heats up the sugar solution to 70 to 95 degrees Celsius, which separates the heavy precipitates from the juice in the clarifier. Heavy precipitates are formed, which is separated from the juice in the clarifier. Insoluble particle masses called mud is separated from the lime juice by centrifuge. Next slide, please. The third major unit operation is evaporation. The clarified juice is put on vacuum pans to crystallize the sugar. The clarified juice initially passes through evaporator stations, which consist of multiple evaporators. Heat transfer process occurs in the evaporators. The temperature decreases due to heat loss from evaporator to evaporator. The pressure inside each evaporator also decreases, which allows the juice to boil at the lower temperatures in the subsequent evaporators. The syrup leaves the last body continuously with about 65% solids and 35% water. Next slide, please. The fourth major unit operation is crystallization. Crystallization takes place in a single-stage vacuum pan to produce sugar crystals from the syrup. The vacuum pan boils the syrup until it reaches the supersaturation stage. As soon as the saturation point has been exceeded, small grains of sugar are added to the pan, which are called strike. The growth of the grains continued with the addition of water until the pan is full of crystal and syrup. As the crystals are formed in desired size and concentration, it is known as masticate. Next slide, please.
Next is centrifugation. The masticate obtained is processed in the centrifuge to separate raw crystal and molasses. The centrifuge spins the masticate in a perforated basket at the speeds of up to 1,200 RPM. And when the masticate valve is closed, the basket accelerates the spin and is followed by breaking at the end. The final molasses is discharged into storage tanks, and the sugars are led to downstream conveyors. Centrifuges are usually operated by AC motors rated from 90 to 630 kilowatts. They usually have high torque motors that save time and improve productivity. Next slide. In depolarization and conditioning, due to plant pigment, reactions with amino acids, and reduction of sucrose, the refined sugar has some coloration, which is usually yellow-brownish in color. Due to high volume of crystallization and drying, moisture is re-released from the sugar that makes it wet again. Conditioning is carried out to remove excess moisture in sugar by having air currents pass through it. In packaging and bagging, refined sugar is stored in silos and then packaged in different capacity bags and then transferred to required stations. Next.
So let's talk about the importance of process control in sugar production. The production process consists of a combination of huge control loops, cascade as well as multi-loops, and input variables in the system. The process requires continuous monitoring and control of the nonlinear process parameters to maintain the process stability, labor safety, and improve the production rate. All the main operation units have their own individual control loop to establish a connectivity with its previous and oncoming process unit. Next slide.
There are three major unit operations that are selected and that we have selected, and their control loops are studied. The major unit operations that we selected are purification with evaporator, centrifugation, and crystallization. The current control strategies are explained in the next few slides. Purification is carried out to remove water content and increase concentration of juice. The variables identified in this control loop are the manipulated being temperature, controlled being volume of evaporators, and the disturbance being the sudden change in juice flow rate. Next. This is the control loop sketch of the evaporator in the purification system. As is shown, the input enters the system, passes through the PID, and then goes through the process function and the disturbance. Next. From supporting articles, it has been found that these are the GP equation, GD, and the PID values. Next. This is the sketch which shows the transfer functions being entered and labeled. Next. This is the Simulink diagram which shows how the control loop is carried out. Next. From the initial PID values of 0.4, 0.005, and D equals 20, it is shown that this is the graph, and it shows that there's only a reaction towards the end of the graph. Next. There are many ways to improve process controls, and some of the ways to improve are to increase loop rates, carry out gain scheduling, which involves using a range of PID values, which are more suited to each moment of the operation, using adaptive PID, which adapts the PID values by considering the input and output changes according to the situation. And the selected improvement that we have chosen for this control loop is to adjust the PID values to be more favorable to the operation. And these are the new sets of PID values that I have. Next. From the first set of PID values, where we change D to 0, it is shown that the graph becomes steadier. Next. And when I is 0 and D is 0, steady state is shown at around 60 seconds. Next. By comparing the last two graphs in the initial graph, it is shown that the graph becomes more stable, and when D is 0 as well, steady state is clearly shown. Next.
Next, we will look at the centrifugal temperature control. This image shows the current control strategy for a centrifuge using heat exchanger principle. Next. These are the variables identified for this unit operation. The control variable would be temperature of the output. Manipulator variable would be flow of steam, as it corresponds to the amount of heat supplied. And disturbance would be the flow of steam. As steady state is assumed, disturbance can be neglected. Next. This would be the graphical representation of this process in Simulink. Next. A closed-loop transfer function can be developed from the process block diagram. As GIP, the transducer does not take part in the reaction, it is neglected, and sensor GM can be assumed to have no impact to the process. Next. To form transfer function GP, data from a research article was used, as seen in the graph at bottom right corner, and time constant and date time could be found. Next. Similarly, control valve function GV can be found with parameters related to size of valve opening, length, area, and pressure. The gain was found to be 1.25, and time constant was found to be 3 seconds to travel 15 mm. The final transfer function is shown on the right. Next. A final plot diagram has been constructed in Simulink, and input was set as sine wave as the temperature input varies over time. Next. PID values was found with transfer function using Zn method. Next. PID values from the last slide was set into the controller, and the diagram here shows the output. The process is proved to be stable, and in steady state is achieved in 750 seconds. Next. To improve centrifugal temperature control, PID controller calibrated with ITSE genetic algorithm was used. The end result proved to be 66.7% faster, as it achieves steady state in 250 seconds, compared to 750 seconds with conventional PID control. Next. Also, since flow rate of steam can be neglected in steady state, transfer function for valve can be removed, and it achieves steady state in 150 seconds, which is much faster. Next.
The final process being discussed here is the crystallization process. There are many stages in the sugar crystallization process, but the one I'm focusing right now is at the final part, which is to convert the concentrated syrup into sugar crystals. As you can see, the variables for this process is chosen as follows. The manipulated variable is the syrup feed flow rate, the constant variable is the volume fraction of crystals, and the disturbance variable is noise. The reason why the syrup feed flow rate was manipulated is because if it's not achieved at a high flow rate, the crystal content remains low and the end sugar crystals wouldn't become too viscous as needed per requirement in the industry. The constant variable is the volume fraction of crystals, because the process after this will be the formation of crystals, and a specific size will be required in producing such crystals. And for the disturbance variable, the disturbance here will be noise, and this can affect the crystallization phenomena as it could affect the crystal growth. Here is the exact process in the crystallization process. Here is a closed loop, and as you can see, we have the PID controller going through the process controller until it reaches the end product, and you can see there's a disturbance input as well. Here are all the values being attained by all various numerous articles, and as you can see, the assumption taken here is that Km is equals to 1. Based on a few articles, it is shown that most of the loop back into the set point is very fast. Hence, I can take the assumption that Km is equals to 1. And as you can see, the Kp and Kd value is derived. And here is the closed loop function with the transfer functions for their specific needs like Kp and Gd. Here is the closed loop function done in the Simulink software. And once that is done, I've run it in the simulation, and it is seen that steady state is achieved at around 70 to 80 seconds. One of the ways to improve the crystallizer is by applying a linearization method, which is the neural network method. This PID controller currently can't handle such linear processes like the sugar crystallization, like this one. So a new PID algorithm can be implemented directly without any modifications. The proposed method, which is the neural network method, can be changed quickly in response to any process change happening inside the entire loop. First, the data will go through the neural model where multiple equations are being placed here. And once a value is linearized, it will be sent to the linearized model to allow a piecewise linear PID parameter. And then it will undergo the optimization to determine which parameters is best suited for the current situation being faced by the control loop. And finally, it'll be applied back into the PID controller so that it can change the parameters to achieve the output needed in the industry requirement. And that is it from our group 4. Thank you.